Welcome to my talk about ROP mitigations and control flow guard. So you can expect something about code reuse attacks. I give you a quick refresher. Then I will talk about emits, ROP mitigation techniques, and as a third bullet point, I will talk about Microsoft Control Flow Guard, the compiler feature. My name is Matthias Ganz. I'm CTO and co-founder of X4 Lab. We are an ETH spin-off. We're building a software product to detect file-based software exploits. You probably heard of this year's Pwn2Own competition. It happened in March this year. And all of the most current browsers, namely Chrome, Edge, Safari, with most current security mitigations have been owned, and system or root privilege has been achieved. So attackers could execute arbitrary code. As an attacker, before you do the attacking, you do some basic math. According to Microsoft, your attacker return, so the money you actually get, you calculate it by the gains per use. So how much money can you steal with an attack times the number of thefts. But of course, you have some costs. So you have initial costs to acquire maybe a vulnerability. So either you do some maybe fuzzing, or you do static or dynamic analysis of your software you want to exploit. And of course, you need to subtract the costs of weaponizing the vulnerability. And this is exactly the point where we, as defenders, try to raise the costs of an attack. So such mitigations to raise costs is, as already mentioned, is emits, ROP mitigations, which are runtime mitigations. So you deploy these mitigations into arbitrary Windows processes. And the second mitigation is control flow guard. This is a compile time mitigation, which is compiled into your program and then checked at runtime. This requires some more or less recent Windows versions. But before we start, I give you a quick refresher on data execution prevention and address space layout randomization and how an attacker can bypass this. So a quick refresher. So data execution prevention, what is it? This is you mark areas of your virtual memory, you give it permission flags. So typically, you have your code section in your virtual memory is typically readable and executable. Your heap and stack is typically readable, writable. So attackers who place code like on the stack, like this has been done some time ago. This doesn't work when you have data execution prevention enabled. But instead of placing code on a stack, you do so-called code reuse attacks. So there is various techniques. You can do return to lib attacks, or the more generic form of this is return-oriented programming. I will get to this. And a similar form, but a form which doesn't rely return instructions, is a jump or call-oriented programming. And the basic idea is to use like existing code until you can, as an attacker, until you can make a call to some functions, like memory functions which change the protection flags of your memory. So typically you do return-oriented programming until you find a call to maybe virtual protect, and then you can mark any piece of memory you want executable. So return-oriented programming, how does it work? You have a so-called ROP gadgets. These are arbitrary sequences of instructions which end with a return instruction. So for instance, these three guys. And return-oriented programming just puts the start addresses of these gadgets to a memory locations, and like an attacker can craft like a puzzle, craft its own functionality by using already loaded code. So how does ASLR work? How to bypass ASLR? So address space layout randomization. This is where we randomly place stuff at different locations. So bypassing it, you may think of if there's a weak implementation of ASLR, you can just try to brute force it, or you try to construct a memory leak some addresses of some useful functions, or depending on the application you want to attack, you can force the application into some predictable memory state by, for instance, applying memory pressure. Another techniques is like pointer inference, or you can try to not use the randomized parts of your addresses in your gadgets. So this would be, you avoid using exact addresses. These both techniques, data execution prevention and address space layout randomization, these are rather generic defense techniques and are widely adopted in x86 world. So this is exploit writing has become harder through these techniques for like most classes of attacks. And together, if implemented right, this is quite an effective defense mechanism. But as we've seen in the point-to-own slide, it's not effective enough. So how do we measure the security of an exploit mitigation? Or how much do we increase the cost of an attack when we enable specific security features? So quantifying this stuff is rather difficult, and academia as well seems to somehow struggle with this question. For this talk, we tried a different, more practical approach. We constructed a program, an exploitable program, and tried out how hard it gets when we enable specific security features like emit, ROP mitigations, or control flow guard. So we hope to understand these mitigations better. So let's start with code reuse attacks. First, the example. We created an example program. We called it mainframe inventory. This is a vulnerable C++ program. It's exploitable by design, but still, as an attacker, you still need to bypass address space layout randomization and data execution prevention. So we created this mainframe inventory program as a 64-bit program. We compiled it with Visual Studio 2015 on Windows 10. And what it basically does, we keep a linked list of programs, of arbitrary objects, and maintain this list and expose a HTTP interface to clients. So this HTTP interface, with this you can create new programs or list them or start programs. So for instance, this HTTP request would create a new program with some specific ID. So this is how the program class looks like. So we have a few attributes like status, ID. The length of ID indicates the number of bytes which are valid in this ID array. Then we have a pointer to a state buffer, and again a state size, which indicates the number of valid bytes in state buffer, and the pointer to the next entry in our linked list. And of course, we have some fancy method, which is by accident virtual. In memory, this looks like this. We have the object P1. We have a pointer to the V table of the program, and then the attributes follow. So an example request like this would create a new program object program object with some specific ID and some specific state we can define as a client. So in memory, this looks like this. We have the attributes here. We have a pointer to the vtable of program. What an important side note, this vtable is located in the read-only data section of the executable. And here, the first entry of the vtable is the program's main method. So we have some pointer to state buffers, so there is some more data which we can control as a client. So, but you already think this may look fishy. So why the heck can we set the ID length? So the programmer forgot to check ID length. So as an attacker, we have control over the length of this ID field, which indicates a number of bytes in your ID buffer, which has a fixed size of 8 in this example. So if an attacker provides an ID length bigger than 8, we can read and write after this ID memory section. So what do we get out of this? We can leak memory, we can construct an arbitrary read, we can deliver some payload, and eventually we can hijack control flow. So how do we do this? How do we leak the memory? So we could set the ID length to 32. So this would allow us to read and write the stuff which is indicated in blue. Writing stuff would do the other thing. So an arbitrary read would, to have an arbitrary read, we would set ID length to 24, assign the number of bytes we want to read, assign it to state size, and the pointer we want to read, we would assign to state buffer. And reading the state would then read our desired memory address. Delivering payload also is easy. We just use this state buffer to deliver arbitrary payload. And we can use the memory leak to read the address of the state buffer. So how do we do the control flow hijacking? We use, if we could create a fake object, which would look like this, we could give it a fake vtable, and the first vtable entry would point to our escape location. So let's try to construct this fake object. We have a sane object, P1. In the state buffer, we place our fake vtable. We create another buffer with our fake object, which now knows the address to the vtable we previously leaked. So we have constructed the fake object. When we update the next pointer, we can successfully insert this new fake object into the list of programs, objects. So hijacking control flow is just calling the virtual method of this fake object. So this would then be some HTTP request in this example. So, but still, we need to bypass data execution prevention and address space layout randomization. This needs the following steps. At first, we need to leak some base addresses of some libraries we want to use code from. We need to deliver our shell code. We need to deliver the ROP chain. We need to hijack control flow to our first ROP gadget, do some stack pivoting, and then our ROP chain will call virtual protect and marks the payload executable, and then we can return to our shell code. So how do we leak the base addresses of our libraries? So if you have two objects, next pointer points to the next object, which at the offset 0 has the vtable. So we just follow this vtable pointer, and we will find the address of the main function in the executable. Since we know the executable, we can calculate the offset. We know the offset of this main function in the executable because this is static. We can derive the randomized base address, and this gives us the image base address. With this base address, we can read the import address table this executable. And in our example, we have like imports. So we use functions. This executable uses functions from, in this example, kernel 32 and some CPP REST library. So we can leak more addresses. So with this, we can say address-based layout randomization is bypassed. Exploit delivery is in example quite easy. We just use this state buffer and leak the address of the state buffer. For this inventory example, we created the shellcode with Metasploit. We use Windows exec shellcode with which pops a calc. Yeah, so this is standard generated code. Then the ROP chain is also pretty straightforward. We use some basic gadgets to prepare our arguments. Like this prepares argument 0, argument 1, etc. Here, for instance, you see the third argument to virtual protect. And eventually, we call virtual protect and return to the shell code. So how do we actually then hijack control flow? We have this is the call site which we want to hijack. So if you look closely, this points then to our fake object. The fake object, the pointer is dereferenced, and now Rex points to the V table, and eventually we call the first entry in the V table, and so control flow gets hijacked. Our first target after hijacking is a so-called stack pivoting gadget. We try to get control over the stack pointer. So the first gadget looks like this. When you as you remember from the previous slide, Rex contained the V table address. So this would load the second entry of your V table and put it into the stack pointer. So if we put the address of our ROP chain into the second entry of our fake V table, we can pivot the stack pointer to our ROP chain. So this will happen. So the exploitation in pictures, we have a normal code, normal stack. We deliver the shell code on the heap. This is non-executable code. Then we deliver the ROP chain, also non-executable. Then we hijack control flow, pivot the stack to point to the ROP chain. The ROP chain gets executed. And eventually we end up in a virtual protect call, which marks the code, the shell code executable, and then executes our shell code. So data execution prevention is also bypassed. This is some screenshot of our demo program. We could pop calc. So next topic, let's enable ROP mitigations for our exploit. So what is Emmet? Before we start, Emmet was introduced in 2009, and the most current version is 5.5, and was released end of January this year. So Emmet implements various security-related features and hardening techniques which you can apply to arbitrary processes on your Windows desktop machine. But for this talk, we will focus only on ROP-related mitigations. This is the Emmet config GUI, if you don't know it. So you can configure processes to be guarded, and you can enable specific security checks for your processes. So ROP mitigations are these stuff in the boxes. We will focus on this. The ROP mitigations were introduced through ROPGuard. ROPGuard was as a Microsoft Blue Hat, won a Microsoft Blue Hat prize, and this ROPGuard was integrated into Emmet, firstly integrated into Emmet 3.5. If you know Emmet, there is some ROP mitigations which are only available for 32-bit. So some of the ROP mitigations, namely the color checks and simulated execution flow, is not available for 64-bit. But before we continue, how does emit the hooking? So emit injects a DLL into every process you want to have secured. So it injects a DLL and then hooks into sensitive API calls. So these sensitive API calls are virtual protect, load library, create process, etc. There are about, I think, 50 functions which are protected by emit. So if we talk about ROP mitigations, there is rather a ROP detection than ROP prevention, because the ROP checks are only done when you call these critical API functions. So how does an emit look like? If you call, for instance, virtual protect, and if you follow the debugger, you will notice a weird jump at this symbol. So this is an emit hook. This jumps to some dynamically generated code. And if you do some more debugging, you will see that the emit code eventually jumps back to the code you want to have called. And this next location has another emit hook. And there is, like, on every level of API call, there is this emit hook, even for the right before the system call. So even system calls are guarded by emit. So this is emit deep hooking, and it prevents an attacker from just skipping over some hook and like call the next lower function. So this should prevent this. So these ROP mitigations, let's start with the first mitigation, the memory protection mitigation. This is fairly easy. Emit just disallows the program from marking the thread stack executable. So placing your shellcode on a stack and mark it executable will not work anymore. And the next mitigation, caller checks. During an ongoing ROP attack, functions are not called, but they're rather returned into. So emit checks the call side if there's actually a call instruction. So when emit does the check, it checks the stack pointer, like it checks the top of stack, reads the return address, follows the return address, and checks the previous function, whether this is a valid call to the hooked function. So it checks, is this really a virtual protect call? Then the next mitigation is a simulated execution flow. And according to documentation, this should detect a ROP gadget following a call to a protected API. So this, we're not 100% sure what it really does, but it seems to simulate instructions affecting the stack and the base pointer and does some sanity checks on them. So next mitigation is stack pivoting. Emit just checks if the stack pointer is within the bounds of the stack, which is of the expected stack. So emit detects any deviation, like stack pivoting attack attempts. The next mitigation is export address table access filtering. This is not really an ROP mitigation, but it makes a lot of off-the-shelf code, like Metasploit exploits it prevents them, because the export address table access filtering, it checks read accesses to the export address table of the 3 critical system libraries. So it checks access to kernel 32, anti-DLL, and kernel base. So whenever someone wants to read a few bytes of this export address table of these 3 functions, emit triggers. So emit does this by inserting hardware breakpoints. And then there is AIF Plus, which is some blacklisting of specific modules to further prevent reading of this export address table. And recently there has been a lot of talks and publications about emmet bypasses. So you can read up on this if you're interested into. But basically, bypassing emmet is you have two options. Either you try to disable emmet. This has been shown for emmet version 5.2, I think, where an attacker could just call DLL unload of emmet, and then emmet did some nice unloading of itself and deinstalled hooks, basically. So you could disable it by calling disable, basically. And this, I think they fixed it in version 5.5. And the other option you have to bypass emmet is to harden your exploit and make it emmet aware, so it withstands these runtime checks. So how do we bypass emmet memory protection? This is the feature where we prevent the stack from being marked as executable. So we just deliver the shellcode not on the stack, but on the heap. Or we just use return-oriented programming and code reuse attacks and not rely on marking any memory as executable. Yeah, and there is another way we found out about. We constructed a sample program which allocates some stuff on the heap with some meaningful, non-meaningful, but valid x86 code, and then we called it. And you see emmet is enabled, so the emmet library is loaded into the memory. The emmet checks are enabled, but we still could call the function located on a stack without emmet complaining. So if we cannot we cannot talk about it yet because we are still discussing with Microsoft, but if you're interested, come by after the talk and yeah, let's see. So how do we bypass caller checks? To bypass caller checks, we just use gadgets that begin after a call instruction. Maybe this is tricky. I didn't actually try it, but this may be tricky. And so your ROP gadgets may become larger and maybe more complex. And we also found some issue on these caller checks. We also cannot talk about it. Yeah, whatever. So stack pivoting, bypassing stack pivoting is you just make sure if you enter one of these critical functions, which emmet protects, you just make sure that your stack pointer points to the stack actually and not to your fancy ROP chain somewhere on the heap. Another option would be just deliver the ROP chain to the stack or copy the ROP chain from the heap to the stack. You could do this with ROP code. So yeah, how to bypass AIF? Since AIF was, this is checked with some hardware feature, there was some guy on the internet which explains how to disable this hardware feature. I'm not quite sure whether this works in most current version of emmet, but it should, I guess. Yeah. So let's harden our sample program, which I introduced before. Let's harden it with emmet, because the sample program is 64-bit. We have to. There is less mitigations for 64-bit. So let's enable it. And then we see that our exploit doesn't work anymore, and we get an emmet violation about stack pivoting. So emmet detected that the stack pointer was out of bounds for this virtual protect call. So having our ROP chain on a stack doesn't work anymore. So what we do instead? What do we do instead? We use the first ROP chain to copy a second ROP chain to the stack. And then we pivot again. We pivot the stack pointer again back to the original stack, but to a different location. And now we can call the virtual protect function, and Emmet will not complain about stack pivoting. Yeah. Yeah, for this example, we used memcopy, but you could do simple roping to copy stuff byte by byte. So we tried this, and we hit the next Emmet violation. So this was a export address filtering violation, because our shell code scans through the export address. Again, we have some detailed information, more or less detailed. So instead of using the Metasploit payload, we constructed our own payload and tried again, and this time it works, so no Emmet complaining. So for our constructed example, bypassing Emmet was somewhat easy, because there are no caller checks and no simulated execution flow checks in 64-bit. This memory protection issue was not didn't really matter for our case, and stack pivoting checks could be bypassed by copying the ROP chain, another ROP chain to the stack. The AIF check was bypassed with some custom shell code, and with some more engineering you could make this. Like the custom shell code now relies on specific library versions, but with some engineering you could make this more reliable. So let's enable Microsoft Control Flow Guard for our example. Control flow integrity is not too new, so the original publication was in 2005, and there has been many CFI implementations proposed since then. So some were compiler-based, there was some binary-only implementations, and so forth. And the basic idea about control flow integrity is to restrict control flow transfers to some limited set of allowed targets. So the first adoption, the practical adoption of control flow integrity was Control Flow Guard, and it's available with Visual Studio 2015 on current Windows versions. And it restricts indirect calls and indirect jumps to a static global set of valid functions, valid targets, which are functions. So how does this look in code? We have a 32-bit code. So this is a function call, an indirect function call without guard. And this is a function call with guard. So you see some additional overhead code. You see this check function, which checks the indirect call target, whether this is in the set of valid targets. 64-bit is basically the same. So this function checks whether the target is in this global set of valid functions. And this introduces some runtime overhead, of course, and some memory overhead, because the implementation looks like this in pictures. So we have the compiler. The compiler generates a list of valid functions and puts it into the binary. And during runtime, this list of functions is like compressed into a bitmap and put into memory. So we have a bitmap of, I get to this later. And also we have the guard check, like this check function which guards every indirect call or indirect jump. So what about this bitmap? How does it work? So this control flow guard bitmap, so one bit of this bitmap covers 8 bytes of addresses in your virtual address space. So here we lose some precision. So actually, I get this is now. So when we transition from this set of valid functions to the bitmap, we lose some precision by the implementation gets rid of the least significant 3 bits, basically. So if you have a 1 in this bitmap, this means the address you've been checking is a valid indirect control flow target. So this bitmap may become large. So for instance, for 64-bit, I had a look at this bitmap. So I used sysinternal's VM map, and you will find a 2 terabyte chunk of memory which is reserved but not yet allocated. So it's reserved. So this is how this bitmap looks like, and some parts of it are like allocated, and this is where your control flow integrity information is encoded. So this bitmap is shared across all your processes on your Windows machine. So you have some shared memory, and some part of this bitmap is for private use only. So if you load a library which is shared among all processes, your zeros and ones end up in some blue parts which you share for all. And if you have like private code, you don't share this. How do you bypass control flow guard? Last year there has been some black hat talks about bypassing control flow guard. And the essence basically was you search for unprotected indirect calls or indirect jumps. Some guys found some in in dynamic code, so just in time compiled code. This was the case in some old Flash version. Excuse me. So you search for unprotected calls or jumps, or you search for CFG disabled modules. So like old libraries which have control flow guard, which have not enabled control flow guard. So when the loader loads a legacy module which doesn't support this, it needs to fill this CFG bitmap with ones, and basically needs to allow any indirect control flow transfer to this legacy module. Or another way to bypass control flow guard is just don't use calls and jumps and use returns. So if you can control the stack or part of the stack, you can just hijack a return instruction, because returns are not protected by CFG. That's what I mentioned before. So legacy modules have the CFG bitmap initialized to 1, so you're allowed to jump and call anywhere you want. And another problem of CFG is this imprecision, because you have a trade-off between memory consumption of your bitmap and precision. So if CFG allows a function at address 420, for instance, to be a valid call target, you allow by implementations all these addresses, like 7 more addresses, to be jumped or called to. So you have some imprecision there. And another bypass possibility is just call functions. Like critical functions like winexec are not, you can still call them. They're not protected. They're protected by CFG, but you're allowed to call them. So let's assume we have no control over the stack as an attacker, and we can hijack some indirect call which is under CFG protection. So we tried to look for gadgets which are still reachable because of this imprecision. So how many gadgets do we still have to work with? So for this, we used some ROP gadget finders. In this case, we added some features to a ROPper. Maybe you know this. This is some Python module, and we made it CFG aware and looked for CFG aware gadgets. So, and we noticed that for Windows 10 64-bit DLL, the number of gadgets reduced from about 20,000 to factor, like reduced by the factor of about 8 to 2,500. So we have still 2,500 gadgets which we are allowed to jump or call to, despite of the CFG checks. And for a very small program, we observed that the gadget count reduced to, in this case, to 3. And we also noticed that if you enable incremental linking, this is a Visual Studio linker flag, the gadget count reduced to 0. What? So what is this incremental linking? So this is a linker flag, and this is for programmers to have a faster linking time with small code changes. So you don't need to wait for your compiler the whole day. And this incurs some runtime and memory overhead, and it obviously helps CFG reducing number of valid targets. So why is this so? So this is an incremental linking table. You have at the start of your code section, you have a table, a jump table, which contains jumps to module intern. So if you do a module intern call or a jump, you use this linking table and do a detour over this table. So if you enable incremental linking and CFG, this table looks like this, and Visual Studio pads this stuff with breakpoint instructions, with interrupt instructions. And now CFG valid targets are only under CFG. You're only allowed to call these functions. And you can imagine on your own, if you look for a ROP gadget, this is pretty hard to find any useful ROP gadgets here. So this is why incremental linking reduces the number of CFG aware gadgets. Another thing to have in mind for control flow guard is dynamic code. So most modern browsers and your Java hotspot does it. It generates code at runtime. So when you do this, you allocate some executable memory to be backward compatible. Your CFG bitmap needs to be initialized to 1. So you want to allow any indirect control flow transfer to this chunk of memory. Okay. So Microsoft introduced some new memory protection flag to harden JIT and proposed and gave the programmers some new functionality to specifically take control over the CFG bitmap. But the take-home message is your JIT compiler or your JIT code needs to be aware of CFG. So this is, again, how do we bypass CFG? We tried to, so we applied to our sample program, we applied control flow guard, and now our indirect call to the program main function is now guarded. Our exploit obviously fails because our first stack pivoting gadget is not CFG valid. So we fail. Yeah. So is this the end of code reuse attacks? Probably not. But these ROP mitigations and control flow guard, they definitely raise the costs of weaponizing your vulnerability. So take-home message, install limit. The CFG stuff, this still needs time to reach end users and to reach the end users. And as a programmer, if you generate dynamic code, as a programmer, do use the CFG. It's a nice thing. And if you generate cheat code, take care. There's a lot of pitfalls. And you need to be aware what you do when you generate dynamic code. And in the future, you may or may not see a shift towards data-only attacks and less code reuse attacks. Thanks.